delving into the depths of the human mind reveals astonishing horizons. Today, we explore the psychology of decision-making, a process that accompanies us daily, from waking up in the morning to falling asleep at night. Each day is filled with countless choices. Some seem insignificant, such as choosing clothes or breakfast. Others, however, can fundamentally alter our lives, determining a career path or place of residence. But what exactly happens in our minds when we face the need to weigh all the pros and cons, assess potential risks, and finally make a choice? Is this process always rational and logical, or do emotions play a far more significant role than we tend to believe? In this exploration, we will delve into cognitive biases, heuristics, and the impact of emotions on our decisions. We will also touch upon the concept of decision fatigue and its effect on our ability to make sound judgments throughout the day. Stay with us to uncover the hidden mechanisms underlying our everyday choices. Gazing at the twinkling stars in the night sky, astronomers of the past could hardly have imagined that stars exist in space whose teaspoonful of substance would be more massive than an entire mountain, or believed in the existence of objects so compact that nothing can escape their gravitational pull. And while this sounds incredible, today it is a reality. Nevertheless, few modern astronomers would claim that we have seen everything and that space can no longer surprise us. In fact, existing theories of the universe predict, or at least do not rule out, the existence of objects that might seem too fantastical to be true. In some studies, scientists mention them, as it is sometimes difficult to explain observed phenomena based solely on the known characteristics of stars, black holes, or planets. In a recent study, a group of astronomers put forward the hypothesis of a possible discovery of a so-called boson star, composed not of atoms of ordinary matter, but of dark matter particles. What exactly is it, and does the universe truly hide undiscovered, strange forms of stars? To begin, it's worth mentioning the space observatory named Gaia. Launched in 2013, it is undertaking the ambitious mission of creating a three-dimensional map of our galaxy. To do this, the spacecraft has been precisely measuring the radial velocity of stars for many years. According to the European Space Agency's website, analysis of data obtained from Gaia allows us to understand how and where approximately 1 billion stars in our galaxy are moving. And while this number seems vast, it represents only about 1% of the total number of stars in the Milky Way. So, in the latest catalog of observational data, among millions of moving objects, astronomers noticed a star whose behavior seemed quite strange to them. The star itself is typical and even very similar to the Sun. It has 93% of its mass and an almost identical chemical composition. However, it moved as if orbiting a dark companion with a mass slightly less than 10 solar masses, at a distance of 1.4 astronomical units. Seemingly, nothing unusual. Most likely, the dark companion is an ordinary black hole, as similar systems have been discovered before. Indeed, most astronomers were inclined to believe that this was another binary system consisting of a star and a black hole. If so, the dark companion is the closest known black hole to the solar system, located at a distance of 1,600 light-years. However, in a new study published in April, a group of astronomers decided to consider an alternative hypothesis. From the perspective of orbital characteristics, the system raises no questions. The dark object can indeed be easily explained as a black hole. But how could such a system have formed? This is an interesting question. According to one of the study's authors, Alexander Pombo from the Institute of Physics of the Czech Academy of Sciences, considering that the formation of a black hole is a rather dramatic event, accompanied by a supernova explosion, it seems strange how the companion star could have survived such an event. Besides the explosion itself, immediately beforehand, the massive star expands into a red giant, and could essentially easily engulf its smaller companion. Of course, one could assume that the black hole simply gravitationally captured its neighbor. However, the star's orbit passes too far from the black hole for this scenario to be considered realistic. For gravitational capture, the black hole and star would have had to approach each other at a much closer distance than they are now. Another possibility is that the yellow dwarf might have originally been part of a binary star system, and the black hole, approaching them, could have altered one of the stars in the system through gravitational interactions. In any case, all these explanations seem unlikely, which is why Alexander Pombo and his colleagues propose considering an alternative structure for the observed system. According to Alexander, although black holes are well-studied objects, and astronomers have already managed to detect them through both direct and indirect methods, there may still exist other objects capable of mimicking the properties of black holes. And perhaps boson stars are the best candidates for this role. Boson stars, also known as Prague stars, represent another astonishing prediction of general relativity. They are part of a broader class of objects called exotic stars. The presence of the word star in their name should not be misleading, as their similarity to ordinary stars is limited solely to their spherical shape. Essentially, they are clumps of elementary particles called bosons. But what exactly is a boson? The modern Standard Model, which most accurately describes the microcosm, divides elementary particles into two main categories, fermions and bosons. Fermions serve as the building blocks of all ordinary matter, forming atoms, molecules, planets, stars, and galaxies. Fermions are also classified into quarks and leptons. Quarks are perhaps familiar to many as the constituent parts of protons and neutrons, which form the atomic nucleus. Among leptons, the electron, orbiting the nucleus, is the most well-known. Thus, all matter familiar to us is composed of fermions. Bosons, however, are something entirely different. They are force-carrying particles that mediate interactions between fermions and regulate the interplay of physical forces. Simply put, they are responsible for the attraction and repulsion of matter. They glue quarks together to form protons and neutrons, and hold these particles together within the atomic nucleus. Photons, the most well-known bosons, carry the electromagnetic force. The famous Higgs boson explains the origin of mass. Therefore, bosons are to thank for extra pounds or the inability to walk through walls. Furthermore, a boson responsible for gravity is theoretically predicted to exist, but its detection has not yet been successful, and its very existence remains questionable. It's important to understand that fermions and bosons obey different physical laws. A key property of fermions is the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state. For example, in an atom, electrons cannot occupy the same energy level. Even under immense gravitational pressure, electrons cannot be compressed to occupy identical orbits, nor can protons and neutrons overlap. This phenomenon, known as degeneracy pressure, prevents the gravitational collapse of white dwarfs and neutron stars. It is thanks to these properties that fermions are able to form complex structures, from which almost everything we see is made: houses, trees, animals, planets, and stars. Unlike fermions, bosons can freely occupy a single quantum state. They behave like waves that can superimpose on each other, forming a more powerful wave. Bosons can form collective states, uniting and exhibiting common properties as a single superparticle or superwave. For example, photons, being bosons, can form a laser beam. This is because many photons occupy the same quantum state, allowing them to act coherently and synchronously. But the most interesting phenomena occur when bosons are cooled to extremely low temperatures. This was first achieved in 1995 when a group of physicists successfully cooled rubidium atoms in laboratory conditions. An isotope of rubidium exhibits bosonic properties. The temperature reached was only 170 nanokelvins, just millionths of a Kelvin above absolute zero. Under such conditions, particles transition into their lowest energy state and move extremely slowly, becoming physically identical. Simply put, they transform into a single cloud of superparticles, governed by their own laws. This cloud is called a Bose-Einstein condensate, or BC. This is a truly astonishing phenomenon, often referred to as the fifth state of matter, and it exhibits very unusual properties. The discovery of Bose-Einstein condensates expanded the understanding of quantum physics and led to the discovery of interesting phenomena such as superfluidity and superconductivity. This is a highly fascinating topic that we will certainly explore in more detail in future discussions. For now, it's important to understand that bosons have the ability to merge and act as a single quantum object. An interesting idea is that bosons are ubiquitous and may have filled the universe in its earliest stages. Shortly after the Big Bang, when everything in the universe was concentrated in a small volume, bosons could have coalesced into immense structures under their own gravity, forming giant Bose-Einstein condensates. Naturally, gravity would easily compress a large number of bosons into a black hole. Therefore, to form stable structures, a force counteracting gravity is needed, as occurs, for example, in stars. However, the bosons we know apparently do not possess the necessary properties. Nevertheless, scientists believe that we have not yet discovered all types of bosons that may exist in the universe. Among the many mysteries of the universe, a special place is held by a hypothetical particle known as the axion. Scientists have been trying to detect it for decades, as it is one of the most probable candidates for a dark matter component. This substance, dark matter, poses more questions than answers for modern science, yet its gravitational effect on ordinary matter is beyond doubt. Should axions be discovered, it would represent a true breakthrough in understanding this mysterious substance that constitutes most of the universe. Notably, axions could theoretically possess a property of repulsion and resistance to aggregation even under colossal gravitational pressure. Thus, by aggregating, axions are potentially capable of forming gravitationally stable objects. These objects could resist gravitational collapse while remaining sufficiently compact and massive, similar to white dwarfs and neutron stars. For now, axions remain only a theoretical concept, but if so-called boson stars truly exist and are composed of these particles, it could significantly advance the search for dark matter particles. Despite the apparent hypothetical nature of these discussions, scientists are actively trying to determine whether clumps of exotic forms of matter can exist in the universe, and are even developing theoretical models of their appearance and properties. Specifically, within these studies, it is suggested that boson stars may share many characteristics with black holes, making it crucial to develop methods for distinguishing them if astronomers ever manage to detect such objects. Unlike ordinary stars, boson stars do not participate in the synthesis of chemical elements, and do not emit radiation, as dark matter interacts very little with other particles. Thus, boson stars manifest themselves solely through gravitational effects. Unlike black holes, boson stars should be transparent, as they lack an absorptive surface capable of trapping photons. Furthermore, they do not have an event horizon. However, possessing significant mass, they would still warp spacetime, deflecting photons from a straight trajectory. On the other hand, they can be compact and massive enough to accrete surrounding matter, similar to black holes. Moreover, some boson stars might be surrounded by a ring of plasma, resembling a black hole's accretion disk. Due to gravitational lensing, a boson star with a plasma torus would exhibit a dark region very similar to a black hole's shadow. In September 2020, a group of astrophysicists conducted simulations to determine how plasma disks around these two types of objects would appear and if there would be any differences between them. As a result of modeling the plasma behavior, it was determined that the dark region of boson stars should be smaller than that of black holes, which is due to the presence of an event horizon in the latter. The simulated images clearly demonstrate the visual differences between these two objects. The observed similarity raises a natural question: could previously discovered black holes actually turn out to be boson stars? Based on the obtained data, the study's authors analyzed the famous image of the supermassive black hole in galaxy M87 and concluded that the shadow size is too large to consider this object a boson star. Thus, at least this particular object is a black hole. As an additional precaution, scientists simulated how boson stars would appear in images obtained by the Event Horizon Telescope, which first captured the shadow of a black hole. The goal was to confirm the telescope's ability to distinguish boson stars if they were ever detected. The simulation results confirmed this capability. Thus, the obtained models can be useful for future observations, allowing astronomers to determine the nature of observed objects, particularly when studying accretion disks traditionally associated with black holes. Given that boson stars can be massive, compact, and mimic black holes, The question arises about the possibility of detecting them using gravitational waves. Preliminary data indicate that some gravitational wave signals show anomalies that might suggest the collision of boson stars rather than black holes. Gravitational waves, predicted by general relativity, are ripples in spacetime resulting from extreme cosmic events, such as neutron-star collisions or black hole mergers. Modern gravitational wave astronomy allows for determining the location of a collision, as well as the sizes, masses, and nature of the colliding objects. In 2021, a group of scientists conducted research to explain the unusual behavior of gravitational waves recorded during an event called GW190521. Initially, the signal was interpreted as the merger of intermediate mass black holes, but the characteristics of the gravitational waves proved atypical. Specifically, immediately before the black hole merger, the waves almost completely lacked the so-called in-spiral phase. As objects approach each other, their orbital velocity increases, leading to an increase in the frequency and intensity of gravitational waves, which appears as a characteristic spiral pattern on a graph. Such a pattern is typical for collisions of neutron stars or black holes orbiting each other. However, the detected signal contained virtually no in-spiral phase, which prompted researchers to consider alternative scenarios. They simulated gravitational waves arising from the collision of two boson stars and found that the resulting models agreed well with the observed data. Is the scientific community truly on the verge of a sensational discovery, encountering previously unseen cosmic objects? The question remains open, as the research results presented by scientists only demonstrate a statistical advantage compared to generally accepted models describing the merger of neutron stars and black holes. A similar situation exists regarding Alexander Pombo's work, where the dynamics of star movement in the vicinity of a certain dim object shows striking agreement with a theoretical boson star whose behavior mimics a black hole. But do these exotic objects exist in reality, or are they merely the product of mathematical calculations, existing solely within the pages of scientific papers? The definitive answer to this question has not yet been found. Given that the concept of a boson star is based on a hypothetical class of bosons whose existence has not yet been experimentally confirmed, the author leans towards the view that this theory is overly speculative. Nevertheless, considering the unflagging interest of scientists in exotic objects, it was decided to introduce readers to at least one of them. In conclusion, the author expresses readiness to share information about other peculiar celestial bodies, such as quark stars, and encourages readers to share their thoughts regarding the nature and properties of boson stars. This concludes the narrative. Take care of yourselves and support the armed forces of Ukraine. Glory to Ukraine!